Hey guys, oops, I'm not even on the right slide. This is our lesson. It's an introductory lesson on the fundamental theorem of algebra. And it's a huge theorem in algebra, but the basic idea is whatever the degree of the polynomial is, that's how many solutions you should be able to find. Now, all the solutions aren't necessarily real, meaning there could be some imaginary solutions, or you could have multiplicity, which means a solution repeats. We'll talk more about that later, but I should be able to find that many. And when we have a larger polynomial that we can't really handle algebraically, in Algebra 2, we're going to use a little bit of technology assistance to figure out where to start the problem. So our goal is to whittle a large polynomial down to a quadratic. Once it's at a quadratic, we got this, because we know like 5 ways to solve quadratics. So let's talk about number 1 here. I notice I have no assistance other than here's your polynomial. I want you to find all the zeros or all the solutions. So with it being a cubic, we should be able to find 3 solutions. And we're going to use the fundamental theorem of algebra, the technique of breaking it down with synthetic division. Some of you are looking at that going, ooh, I think I could factor that. You can. But let's pretend we don't know that for a moment, okay? Just to practice using synthetic division. So first thing I would do is go to my calculator. And now you notice I have 2 functions typed in. I did a sneaky teacher thing where I typed my next problem in too, but I de-emphasized the equal sign. So that way it doesn't graph both of them at the same time. It's just going to graph this first one. And speaking of graph, let's look at that. So 3 things I see. 3 important things. It has the cubic shape, so that's nice. I can clearly, I think, identify some zeros. Like for instance, right here, I am pretty darn sure this is at x equals 3. And if I'm not super sure, I could try doing a couple things. I could go to my table and check that at x equals 3, I do indeed have a 0 height, so that means it's a 0. And you might notice there's a couple other ones here too. We have 0 and 1. We'll come back to that idea in a minute. Play along with me for a minute, all right? I'm going to start, and you can technically start with any of them, but I'm going to start with that x equals 3. So on my calculator, so I'm going to write a little note here. We typed this in. And then on my calculator, I saw something like this. Okay. And right away, my eyes were kind of drawn to this one, which is at x equals 3. That's where I start my synthetic division. So if you remember your synthetic division setup, you have this weird little box. And then that number that we just picked from the calculator, this guy, that's what goes in the box, okay? The actual solution. You don't have to do anything with solving or opposites. It's already solved, okay? Then I take my coefficients of my function, but be careful, this one is missing the constant. So our coefficients would be, whoops, that's a 1. 1, -4, 3, and 0. And now we perform synthetic division. So I leave a little line, little space. I'm going to bring down the 1 to start my synthetic division. And turns out synthetic division isn't division at all. It's multiplication followed by addition. So I like to break up my work into columns. You can do this if you want. All right, here goes. Remember, if it's below the line, that means we're multiplying by the box. And if it's above the line, that means we're adding the column. So 1 times 3 is 3. Oops, I forgot to mute that, sorry. And then -4 plus 3 is -1. And then you start all over again. So -1 times 3 is -3. And when we add up that column, I'm going to put little plus signs here. When we add up that column, we get a 0. Watch out here, 0 times 3 is actually 0. A lot of kids don't get that right for some reason. And then 0 plus 0 is 0. So remember in synthetic division, this last number here that you get is the remainder. And then in today's lesson, because we are purposely choosing values that are zeros of our function, the remainder today should always be 0. If you get something other than 0 here, something's wrong, you messed up, okay? So now I think back, okay, I had a cubic and I knocked it down 1 level because I divided it by one of the roots. So this cubic becomes a quadratic. This is now an x squared minus a 1x. I'm not going to say plus 0 because it's weird. And they want me to find all of the zeros. Well, guys, finding zeros means to solve. So my next step, and I'm going to write a few notes to myself here, right? This became this. So now we're going to solve it. Pen. Gosh, I'm having a lot of tech difficulties today, guys. Solving means to set it equal to 0. All right, here goes. So we have x squared minus x equals 0. Now this is a quadratic. You can use any method you want for solving the quadratic, but turns out we like factoring the most. So this is the kind of factoring question where you can take out the common factor. So you have a common factor of x that you could take out of here. And if you took out a common x, you have an x minus 1. All right, we are factored, which means now we get to solve. Take each of your factors and solve them. So this one's easy, right? X equals 0. And this one right here is not too bad. X minus 1 equals 0. So if I solve that, I get x equals 1. So x equals 0, x equals 1. But wait, one of the very first things we said was the fundamental theorem of algebra states that whatever your degree is, that's how many solutions you're supposed to find. We had a 3, right? Wasn't it cubic x to the third? I only found 2 solutions. But wait. There was another one, the one we stole from the calculator. So the x equals 3 is my third solution. We kind of cheated. We used our technology. And I know you're thinking like, Abruzzo, I could have just told you 0, 1, and 3 right off the bat because I saw them. I saw them cross at 0, 1, and 3. That only worked because you had really nice, easy, rational, real solutions. What if our solutions aren't pretty? What if they're imaginary? You won't be able to see them. So that's why we're learning this technique, okay? Let's see what happens next. I bet something really crazy, right? So I'm going to go back to my calculator. I'm going to type this into my calculator, which I kind of already did. Now, if you need to pause and type this into your calculator, that's fine. It's x to the third minus x squared plus 49x minus 49. That's off of your notes. What I have to do is I have to turn on that y4, so I'm going to emphasize it. Now, it doesn't have to be in y4, it's just where I put mine. Okay. Pause the video if you need some time to get to your calculator. I'm going to graph it. I'm only seeing 1, guys. And literally, I'm saying 1. X equals 1 is where it crosses, I think. So I'm going to go to my table and just double check that. X equals 1. Yep, there's a 0 at x equals 1. All right. Well, that wasn't very exciting, was it? So we graphed this on our calculator. And we saw not much. I actually didn't zoom out to see much of anything, but I think what you guys would have saw is something like this, like a weird little cubic that only has this one obvious real solution. At x equals 1, there's definitely an intercept that we found. So that's the number that we're going to use in our synthetic division box. X equals 1 goes in the box. And then we line up, remember, our coefficients in standard form order. This time, they're not missing anything. We have cubic, quadratic, linear, constant. All right. So coefficients are 1, -1, 49, and -49. Leave yourself a little space. Draw this breaker bar here. And then remember, for synthetic division, you gotta start it. So bring down that first coefficient of 1. Remind yourself that if you're below the line, you're multiplying by the box. And if you're above the line, you are adding the column. So one of those magical moments in math where everything builds, right? Okay, multiply. 1 times 1 is 1. And then if we add up that column, we get nothing. 0 times 1 is 0. Careful there. If we add up that column, we get 49. It's the wrong color, Abruzzo. Messing yourself up. And then 49 times 1 is 49. Now remember, we stated in the last question, your remainder on these questions today should always be 0, which we are getting a remainder of 0. So that means we're on the right track. We haven't done anything wrong. This is where it gets weird. Okay, we had a cubic, we knocked it down 1 level, so now we do have a quadratic. So this is 1 quadratic, 1x squared, plus 0x, I'm not going to write that, and then a positive 49. And I want you to remember the directions were to solve, so I'd set it equal to 0. So it is a quadratic. I can use any method I want, but this is a really good candidate. I can't factor this because it's not minus 49, be careful there. This is a good candidate for the square root method. So I'm going to start by subtracting 49 to the other side. And then we end up with x squared equals -49. Okay, it's about to get weird. Remember what happens here? We're square rooting both sides. Something should be happening, something weird, right? X equals, I know a plus or minus shows up right now. The fact that it's negative should be kind of tipping you off to something else that happens in math. Remember, the square root of negative 49. Yes, there's a 49 in there, but there's also a negative 1. So remember, while 49 is just simply a 7, the square root of negative 1 is called an I. We have two imaginary solutions. That's why we couldn't see them. All right, so your solutions are x equals 7i, x equals negative 7i, but wait, this is a cubic. There's supposed to be 3. Remember the calculator? We stole that x equals 1 from the calculator. So write yourself a little note. This one's from the calculator. And the other two we had to find. So that is why we can't be super dependent on our technology all the time, because sometimes your technology doesn't match up with the math. Like you can't see on a graphing calculator an imaginary solution or two, so you have to find them through another method. Great. All right, so that was actually the hard part of the lesson. This part should be nice and easy. We're going to work backwards. I'm going to give you the zeros, and I want you to put them back into the polynomial factored form. And we are not going to like distribute and come up with standard form. I just want you to leave them factored. So when I look here, we got a 0 at 2, 1, and 4. So you should name your polynomial. You can name it anything you want. I'm going to go with p of x. Let's think about this. If I have a 0 at 2, go backwards. What does that factor look like? Wouldn't that factor be x minus 2? And then if you had a 0 at x equals 1, if you think backwards, wouldn't that factor be x minus 1? And then similarly, if you had a 0 at 4, think backwards, wouldn't that factor be an x minus 4? And that's all I need you to do today for Algebra 2. If I gave you solutions, could you write me, leave it in factored form, could you write me a polynomial? So same idea here, guys. It doesn't really get too nasty, does it? If I gave you a 0 at x equals 2, be careful here, if you think backwards to the factor, wouldn't that factor have been x plus 2? And then similarly here, x equals negative 4, the factor would have been x plus 4. And then you guessed it, x equals negative 7, the factor would have been x plus 7. So that wasn't too bad. But of course, they got to throw a little weirdness in it because it's algebra. What if there's an imaginary solution? Well, this is part of the fundamental theorem of algebra. Imaginary solutions come in complex conjugate pairs. So remember that good twin, evil twin idea where like one's plus and one's minus? That's what they mean by complex conjugate pairs. So for instance, if you know you have a 3i, that means you also have a negative 3i. If you know you have, I'm just kind of making this up, okay, 4 plus I, that also means you have a 4 minus I. If you know you have a negative 3 minus 2i, this one's kind of weird, careful, that means you also have a negative 3 plus 2i. That's what we mean by conjugate pairs, where the I component has the opposite sign. So that was just a bunch of examples, has nothing to do with this problem. So here I want you to write a polynomial that has a 0 at, and they start off nice and easy. They say you have a 0 at 8. So if I think back to his factor would be x minus 8. Well, this is where it gets weird, okay? You have a solution at I. So his factor for I would be x minus I, because remember I is like a number. But wait, there's more. His pair shows up. So if positive I is a solution, that means you also have a solution at negative I. So a solution at negative I, his factor would have looked like this, x plus I. So you should see that good twin, evil twin factor setup that we saw back last semester, okay? Yuck! Okay, that's kind of as gross as it gets. The fundamental theorem for Algebra 2. The fundamental theorem of algebra is a huge concept. And it's actually the basis for a lot of your work in calculus as you move on. For some of us, we're trying to get ready for our SAT test, and this is it. But you never know when you need to move on in math when you go to college, guys. So take it for what it is. It's a culmination of a lot of thoughts in math. It's a really great idea, and you can expand on it in your next few classes. I really enjoyed this lesson. I hope it wasn't too painful for you. All right, good luck, everybody.